Good morning, everyone. Welcome to our third talk of the series. It is my pleasure today to introduce our speaker, Professor Molei Tao. Uh, Professor Tao is an associate professor in the School of Mathematics at Georgia Tech. Professor Tao works on the theory and applications of machine learning, nonlinear dynamics, applied probability, as well as Hamiltonian mechanics and optimization problems, and has published a great volume of work on these topics. Professor Tao obtained his PhD from Caltech in 2011 under the supervision of Professor Homan Owadi and Professor Gerald Marsden. Professor Molei Tao has received many awards honoring his work, and just to name a few recent ones, he received the NSF Career Award in 2019, the AI Stats 2020 Best Paper Award, and recently the Colin Peck Scholar Award in recognition of his research accomplishments. The title of his talk today is When Dynamics Meet Machine Learning. And without further ado, please, Professor Tao, begin whenever you're ready, and welcome.
All right. Thank you so much, George, for the introduction. Thank you, everyone, for coming. It's really a nice pleasure to see so many of you here. And one thing that I wanted to say beforehand is that I try to make the talk accessible to undergraduate students, and as a consequence, I may be under-explaining things, or maybe not explaining things to an extent that please everyone. But if there's anything that comes up during the way that you wanted to hear more about, please feel free to interrupt at any point. And also, I don't know whether I will do a good job in telling the story to undergraduate students due to diverse backgrounds everyone can have. So again, same thing. So interrupt me if you have any questions. So what I'm going to talk about, again, because of the nature of this talk, is that I want to first outline some of the philosophy that we have, and then I'll introduce more details. So we are interested in exploring basically interactions between machine learning and nonlinear dynamics. So of course, in the past decade, everyone has seen great success and progress in machine learning. A lot of them were actually coming out of powerful tools in statistics and probability. And I'm trying to argue that all branches of existing theory can be helpful. For example, nonlinear dynamics can actually play an important role as well. And in fact, this is a trend that is actually rapidly picking up nowadays. And to see why there could be a lot of interactions. For example, so if you go in the left to right direction, you can actually use machine learning methods to solve dynamical problems in sciences and computing. And in fact, as the first part of my talk today, I'll showcase one example. So basically, I will be given data, and then I'll try to learn structured dynamics out of the data and use what I have learned to make long-time predictions. So this is actually, in some sense, solving scientific problems, because you may actually not know the science behind the system. You just have observational data, but then by learning this dynamics, you can sort of extract the sciences from the underlying process and make long-time predictions. And also, it serves the purpose of computing, because maybe you have very complicated systems. A typical example, say you have like a lot of particles interacting with each other, but maybe there are some macroscopic closure that you don't really know a priori, but if you can learn it purely from the data, you learn a reduced model, and then you can simulate this reduced model with much better efficiency. So So that's why, something like this can actually also help computing. So that's a forward direction. There is also a backward direction where you can actually use dynamics. So you basically go from the right to the left. So you can use dynamics to help design and analyze optimization, sampling, and deep learning algorithms. So that's going to be part 2 of this talk. Again, this is actually a very big topic. So I'll only be giving one example. So we will be analyzing deep learning algorithms, and in particular, I want to quantify some of the very interesting effects of something called a large learning rate. Roughly speaking, but if you use a large learning rate, you will get better training and test accuracies when you do machine learning. But of course, this is something that needs to be quantified. So these are the 2 major directions, and some examples that I'll talk about. There are a lot of things that I won't be talking about today. So for example, dynamics can help optimization. So I'm happy to tell you more offline. It can also help something called a sampling problem, which is related to other mathematical areas like optimal transport and other machine learning areas like generative modeling. So, sorry that I cannot, take too much time. So let me actually jump right into part 1, machine learning for dynamics in sciences and computing. Sorry. So I'll be just describing one work. This is a joint work with my former student, Yuanyi Chen. It has a very long title, but it's basically on learning the dynamics of mechanical systems. And we will see that if you do it properly, you can actually gain very good prediction accuracy that is also provable. So that's what I'm going to do. But before doing so, you might wonder, why do I want to predict the dynamics of mechanical systems? That's because number 1, our world is mechanical, and number 2, we want to understand our world. So for instance, here is the orbit of a planet that is precessing around a star. So I'm basically drawing an exaggerated situation. So the precession of the orbit is very, very significant. And imagine you are actually Kepler or Newton. So you don't really know the underlying physics that generate those trajectory. Well, this trajectory. All you have is probably like these red dots, which are observations that you collected at discrete time. And what you want to do is to understand the underlying physics as well as make predictions such as the green dots. And if you think about this, this sounds like mission impossible because you want to make very long time prediction. But you actually have some information about the system. So this is a mechanical system. Even though you don't know like the precise formula of say the force, you know that it must satisfy some universal properties. For example, maybe you have conservation of energy, conservation of linear momentum, angular momentum, etc. So if you dig a little deeper, there is an underlying geometric quantity called symplecticity that is actually conserved by the dynamics in general. And this conservation is something that is very, very good. And in fact, this is something that we will build in our learning model. And as a consequence, we will actually gain superior prediction accuracy. And more precisely, here is my setup. So I'm given training data, which are basically multiple time series. So these are, each one of them corresponds to a sequence of observations. So I is basically the discrete time index, and J indicates which sequence it is. And I have a very simple model. So I assume that this time series is being actually generated by the iterations of the evolution map phi. Okay, so this phi basically maps the current observation to the future observation in one step. And the goal then is very simple. I just want to learn this evolution map in order to learn the dynamics. So I have X and I want to learn phi. And then the task of prediction slash forecast is very simple. So suppose now you have a new state of the system and then you want to predict its future, then I simply iterate this map. One thing that I want to emphasize is that it's likely that I want to iterate this map many times. So this is what I roughly mean by a long time prediction. And sorry. And even though the setup that I formulated was very reasonable, that was usually not what people traditionally did. So traditional approaches were largely based on differential equations in the sense that, okay, so people actually assumed there is a latent dynamics generated by some differential equation. And then your observations are really just the observations of the continuous trajectory at discrete time points. And the goal there was to learn the vector field F. But if you think about this, F and phi are not the same thing. So for instance, F points in the tangent direction, but phi directly does the jump. So unless your observation time window is very narrow, meaning that you have a lot of observations, F and phi can be pretty different. But of course, in practice, in a lot of situations, you don't have like infinitely many observational data. So making observations is expensive, and your data is very scarce, but very valuable. So in this case, if you look at this learning dynamics, this learning differential equation approach, you see several sources of inaccuracy. So number one, you have to approximate the time derivative from the discrete observation. So this is numerical differentiation. It basically incurs error. And then you have, say, those time derivatives, and then you have to find a function f that matches this time derivative. So this is a function approximation problem. You have function approximation error. And finally, you want to predict the future. So you have to integrate this differential equation. Because it's a nonlinear differential equation in general, you will incur you will actually create some error. So you have three sources of inaccuracies, whereas if you use just the above approach, the new approach, where you basically learn this evolutional map, you just have one source of error, which is this function approximation error. In addition, I can actually hardwire physical information into my learning model. So what do I mean by physical information? Like I hinted before, the one that I care about is symplecticity, meaning meaning in coordinates that this evolution map has to satisfy this quadratic equation, or more precisely, its Jacobian, which is a matrix, has to satisfy this equation everywhere. So why do I want something like this? Well, that's because this is actually a property of mechanical systems. For instance, if you really have an underlying ODE system, and that's actually generated by a Hamiltonian. So it's supposed to have a Hamiltonian system, which is in some sense a typical way of modeling mechanical systems. Then no matter what your Hamiltonian is, no matter what specific system you have, the evolution map is automatically going to be symplectic, satisfying this equation. So that's why I actually want this symplecticity to be a hard constraint. I don't want this to be satisfied, approximately. I want it to be satisfied exactly. And so the goal that we have is therefore to learn a map phi that generates my observations, and meanwhile having this phi satisfying this nonlinear constraint. And if you think about this, this is actually pretty hard. I mean, in machine learning, what people might be used to doing is that they will penalize the satisfaction of the second constraint, and also penalize the satisfaction of the first constraint. But then you will not be able to find a phi that is exactly symplectic. So that's why we resort to mathematics. So there is actually one way to indirectly represent phi, namely, so given a symplectic map phi, I mean, for experts, I should really say that this is a short enough time evolution symplectic map. And given any such map, there is actually something called a generating function that is in one-to-one correspondence up to some changes to this symplectic map. And how this works is that, okay, so this symplectic map basically evolves the current position and momentum to the future position and momentum. And one example of such a generating function is, it actually relates also the current position momentum and the future position momentum together, however, via a PDE. So it's a funny looking PDE because this S in this case is evaluated at a mixture. So you are evaluating it at the current position and the future momentum. And then if you do this partial derivative and then evaluate, you will get the current momentum. And if you do it in the other way, you get the future position. So I will not have time to explain the profound Hamilton-Jacobi theory behind this. But in terms of execution, then things become much easier because then I will no longer use a neural network to parameterize phi in order to find the phi. Instead, I will use a neural network to parameterize this generating function. And the goal is to find the good parameterization that match the training data. So that's why our approach is called generating function neural network. The way it works is that, again, you pick your favorite neural network parameterized by this parameter theta, and then you basically require your neural network to satisfy these two governing PDEs, and then you minimize with respect to theta. Okay, so you want to find the theta that achieves the best match. So that's how you do it. And one nice property of this is you don't have to worry about symplecticity anymore. So if you can do this optimization problem very well, if you have sufficiently many data, then you can have a very good approximation of the actual dynamics. Otherwise, you can use a very small neural network. You can have very terrible data, and then you don't have a good approximation of the actual dynamics. However, the dynamics that you will get will always be symplectic. That's guaranteed by generating function. So symplecticity is always going to be guaranteed exactly. And because we have a map-based approach and we have exact symplecticity, by using some advanced techniques from dynamical systems, we can prove, and by the way, the technique is called KEM theory. We can prove that under reasonable conditions, we have a quantifiable bound on how much error you can have in the prediction. So here in this error bound, these two quantities are basically the predictions after n steps, and these two are the truth, which you don't know, but you can still assume they exist, and then try to get a distance from the truth, a bound on the distance from the truth. And the bound says, okay, so first of all, you have some scaling by epsilon. What is epsilon? That's basically how good your neural network can approximate a function. And you have actually something called universal function approximation theory, which says that if your neural network is basically large enough, you can make epsilon arbitrarily small. And in addition, these things are pretty important because n is basically the number of steps of prediction, and therefore n times h is the prediction time in physical time. And you can actually have a bound that is linearly growing with the prediction time, and this actually works for very long time prediction. So this linear growth of the long time prediction error is very important because it should be contrasted with traditional approaches. So in traditional approaches, where you basically don't use map-based approach or have exact symplecticity, you can have exponential growth of the error. And this is not because you have a lousy bound. This kind of error can really be attained. So, so you see that, okay, so if n times h is very big, traditional approach will give you a much bigger error than the new approach. So that is why, for example, when we predict planet orbits, our prediction basically has error that stays at the very bottom when compared to other popular approaches on the market. And we can also do other problems. So in fact, the planet motion problem is given by the ODE, but we can also do discrete dynamics. So it's still a mechanical system, but it's not even a Hamiltonian system. And in fact, this is something called a standard map that we are trying to learn. And it actually corresponds to chaotic dynamics. So if you haven't seen this before, I apologize that I don't think I can explain all the details, but roughly speaking, so this is something called a Poincare map. So this is basically something we want to capture, and something that one wants really badly is that in this Poincare map, you have like those regions that are called chaotic seas, and in the chaotic sea, you actually have like those white regions that are stable islands, and we want to basically capture the shapes of those stable islands as well as the chaotic sea in between. So our approach was the only one that sort of captured the major islands, but it's not perfect, but it's already way much better than all the other existing approaches. So so this is a situation where the error bound doesn't even apply anymore, but you still get qualitatively very good results. So so let me summarize the first part. So by using a map-based approach, we invented generating function neural network that has exact symplecticity, and as a consequence, all the three factors, we actually invented KEM-like techniques. I mean, for the experts, we actually invented new things because that's actually KEM theory for generating functions, not for evolution maps. But it's trivial in some sense. The generalization is easy. And then we use this theory to actually prove superior long-time prediction accuracy. Okay, so that's the first part. Maybe I should pause and just in case anyone has comments or questions.
Can I ask a question?
Oh yeah, please.
What about if you're like in a collision zone? So you learn somewhere where you do not have collisions, and then you have initial data which will lead to collision. This will be a problem, right?
Yeah. So if you if the dynamics is non-smooth, if I understood correctly, then I don't know what will happen. So the proof certainly breaks down. In practice, will the method still work? I'm not sure. So in fact, Hongkun Zhang, I know she was actually using this approach to study billiards, but I don't know the updated version, the updated results. So am I answering the question?
I was thinking about planetary collisions.
Oh, okay. Yeah, okay. So I think that's going to be even harder. I don't know.
Molei, can you say maybe for the sake of the students a few words about the property of symplecticity, maybe a little bit more of motivation regarding the physical interpretation of this?
Great. So yeah, sorry, that's a very good point. So so what is symplecticity? So so symplecticity can be roughly understood as conservation of an infinitesimal volume element in the phase space. So that's still abstract and nonsense. So the idea is that okay, so there's something called a phase space, right? So So that's basically a collection of all possible initial conditions, let's say. So, so of course, you can study things trajectory by trajectory. So you pick one point and you see how that point moves in the phase space, and then you get basically you can trace a line, and this line corresponds to the solution. But you can also consider a collection of initial conditions, right? So you can consider an ensemble of initial conditions. Say they are very close, so they form a small volume element in the phase space. And then you evolve each one of them according to the dynamics. And then, this volume will change its shape, most likely. Maybe it'll spread out, maybe it'll shrink, maybe it'll actually, become, I don't know, stretched and then flattened. Well, so maybe it gets stretched in one direction, and then you fold it back. But anyway, so this shape can change, and symplecticity basically ensures that the area or the volume of the element remains the same. So so that means that, for example, you cannot have dissipation. You cannot have anti-attraction, anti-dissipation either. So that's very roughly speaking one important consequence or feature of symplecticity.
Molei, can I ask one more question?
Yeah, please.
For the planet data on top, is it simulated data or it's data from observations?
It's simulated data because
Thanks a lot. Yeah.
Because our approach is a neural network approach, so it's very data hungry.
Right.
Yeah. So there are other approaches. So there's a popular alternative function approximation approach based on dictionary. So you basically have a dictionary, and then you look for coefficients of linear combination from the dictionary. So if your dictionary is very good, you can fit good functions with a lot less data. It just depends on how we represent our generating function. Thanks for the great question.
Yeah, thanks a lot.
I have a follow-up question. When you say simulated data, is it a perturbation from the initial conditions, or is it perturbation from the truth, from the original, or how are you generating those
so
data?
it's actually, yeah. So roughly speaking, it's actually the truth. So you basically have to have a bunch of initial conditions that sort of cover the region in which you want to learn the physics. And then you simulate the Hamiltonian dynamics with high fidelity, so that you produce trajectories that are almost like the truth. And then you use these time series as your training data, because you can only learn what you are given. So if you can give like trajectories that are not really planetary motions, but bad approximations of the planetary motion if you didn't simulate it very accurately. But then then you will learn the bad planetary motion. You will not be able to create knowledge out of nothing.
Thank you.
You're welcome. Okay, if there's no more questions or comments, let me move on to the second part. So in the second part, I want to use dynamics to understand deep learning. And of course, that's a very, very bold thing to say. So we will actually be focusing on some specific problems. So nevertheless, let me first tell you about the paradigm of supervised deep learning or supervised machine learning. It doesn't even have to be deep. So in supervised machine learning, you are typically given something called a training data. In this case, a training data is a collection of pairs. Each pair is basically a pair of an input and an output. And then you take some model modeled by G, which has some parameter X. you basically want to find the best parameter of this model so that this model tries to predict the output, and then you try to match the predicted output with the actual output, and then you get something called an empirical risk or empirical loss, and you try to minimize basically the extent of mismatch. So this is a minimization problem. But if your G function, if your neural network, for example, if you use a neural network, your G function can be very complicated. It's not going to be giving you basically a convex loss function f. So you will be very frequently trapped in local minimizers of f, which it has many, and that means you have suboptimal training accuracy. Okay, so there is a better match, a better parameter that gives you a better match, but you cannot find it because you get trapped in a local minimum. So this is bad. This is bad for machine learning. And in part 2a, I'll argue if you use a large learning rate, which I need to specify, then you can somehow get out of local minima. So this is going to be good for machine learning. And that's why, by the way, in practice, that when people use a large learning rate, you can actually get better performances. So in some sense, this is not only one explanation of what people actually have been observing, but also this is a suggestion of how you should do it. But that's not it. So once you're done with this training phase, you also have a testing phase where this X is already obtained, and then you have new data pairs, which are called tested data pairs, and then you want to basically compute how well your trained model performs on the tested data. And in this case, what you have trained matters. So maybe your F even has maybe you are already at a global minimizer of F, but even if that's the case, it may not be enough because there could be different global minimizers, and which one you use actually matters. So so there is a difference between this training accuracy and the test accuracy, and the difference is sometimes called a generalization. And you want good generalization, but later on I will show you that not all, even global minimizers, will have the same generalization. So some is better. And in part 2b, I'll try to argue that if you use a large learning rate, you can actually go to you can actually pick the ones that generalizes better. So so that's again something that people like in practice. Okay, so let me first describe part 2a. So this is a joint work with student Lin Tai Kong, and again it has a very long title, published in some top machine learning conference. But I'll explain everything, so you don't have to worry about the long title. So the problem is very simple. I want to do minimization of F, and one popular approach people use in machine learning is a very simple iteration called gradient descent. So basically, you just iterate this this rule, and then you are hoping that you will converge to a local minimizer. And if the learning rate H, so H is called the learning rate in machine learning, even though if you're a numerical analyst like me, you probably will call it the time step. They are the same thing. If H is small, then you will indeed be converging to the local minimizer in a very natural way. So X actually converges in a monotonic fashion. If H is very big, much bigger at least, you can still have convergence, but you actually have this oscillatory behavior. So if you know the continuous limit of this, which is something called gradient flow, you see already your behavior is very different from gradient flow. If you make H to be bigger, you can have actually blown up solution. Okay, so your X actually goes to infinity unboundedly. So already you see that, okay, so learning rate, the value of learning rate matters, but that, what we saw earlier were sort of boring. But what if the potential well that we just saw was a small part, a microscopic part of a macroscopic multi-scale landscape? Okay, let's pick a large learning rate and do the same thing. And again, this dot basically traces the location of the particle. So it indicates the value of x in this potential well. So you can see that this particle bounces around. It's very hard to predict where it'll go next in time. And in fact, I plotted the trajectory of x as a function of the number of iterations. It has this trajectory. It looks very random. And I also collected values that x takes along this single trajectory and plot the histogram. You see, some shape, and if you're a statistical person, you may say, oh, this looks like a nice shape. This seems to be a pretty good statistical distribution. So in fact, if you are familiar with machine learning, you know that there is something that people use called stochastic gradient descent, which introduces stochasticity into the system. And the behaviors of the deterministic gradient descent evolution that I just plotted here actually resembles the behavior, the stochastic behavior of SGD very much. So what is exactly going on? So we do have a quantitative theory. The theory says, okay, so if your objective function is multi-scale and you use a large learning rate, and then even if you use a deterministic gradient descent, you can get stochastic behaviors because you will basically get chaotic dynamics. So let me be more precise. So first of all, what I mean by multi-scale objective. So I mean that, okay, so the objective function is a superposition of a macroscopic behavior, for example, something like this, plus microscopic behavior, which is characterized by a small parameter epsilon. So one example of a microscopic potential is that, okay, so you take a periodic function, you squeeze it in the x direction, you squeeze it in the y direction, and then you get basically periodic microstructure, and then you add it on top to the macro potential, and then you get something like this. So practitioners may say, oh, this is just a mathematician's fantasy. In reality, the small scales will never be like this. Well, it doesn't have to be so. So for example, if you assume something called quasi-periodic micropotential, then you can get seemingly much better, much more realistic small scale details. We don't need that either. So in fact, our condition is pretty mild. So we just need the micropotential to have some order 1 first order derivative that has a weak limit. And also there's some condition on the second order derivative. So this is a little technical, so let me not talk too much about it. But just to say the multi-scale objective is pretty general. What about a large learning rate? Okay, so if you write down the gradient descent iteration, under the assumption of multi-scale potential, then the iteration basically looks like this. And you can first ask yourselves, what would be a small learning rate? So in optimization, it's actually well understood that if your learning rate eta is smaller than 1 over L, where L is the Lipschitz constant of the gradient, then you will have guaranteed convergence to a local minimizer. And in fact, you will converge to the closest local minimizer. In this case, you can actually work out the math and see the Lipschitz constant is at the order of 1 over epsilon, which means that if your learning rate is smaller than epsilon, which is the characteristic length of the small scale, then basically you resolve everything. You resolve the small scale, and then you will just converge to a nearby local minimum. So it's usually a microscopic potential well. What about the large learning rate? So what about a bad learning rate? So the learning rate cannot be arbitrarily big. So if eta is too big, then you cannot even resolve the large scale. And then like the animation that I showed earlier, the iteration will be unstable. Even if you discard the stiffness, it can be still unstable. So this is basically a regime you cannot use. But in between, you have a lot of spaces. So so as eta keeps on growing, you will first enter a regime where let me call actually this space in between to be the large learning rate regime. So you will first enter something that we call a local chaos regime. And as eta further increases, you will enter a global chaos regime. So what happens in local chaos? okay, so you can actually look at the iteration of gradient descent. It's actually the iteration of a deterministic map. You can take a dynamical system's point of view. For example, you can look at a neighborhood of a minimizer, and in this neighborhood, when eta is very small, the minimizer is actually going to be the only attractor. It's an attracting fixed point in that neighborhood. But as you keep on increasing eta, at some point, this fixed point will actually lose its stability. So it's still a fixed point, but it's no longer stable. And instead, nearby, you will have actually a periodic orbit of period 2 that bifurcates out. So what that means is that, okay, so if your x is like this value of -1, you iterate this map, then you get to this point, +1. And then you iterate again, you will get back to the -1. So you get a periodic orbit of period 2, and it's actually the attractor in the neighborhood. And as you keep on increasing eta, the periods actually keeps on doubling, and the period actually quickly becomes infinity, roughly speaking, and the system transitions into chaos. At this moment, this X still stays within a small scale potential well. This is a microscopic potential well. And in this case, this map is something called a unimodal map. So there are a lot of existing theories that can help us understand the chaotic dynamics. But that's not it. So suppose you are at some point, at some step right here. So your gradient will, of course, be pointing to the right. And you can easily see that if your learning rate is large enough, then after one iteration, you go out of this local potential well. You can sort of see this. I mean, so as eta keeps on increasing, so this, this region floods. So eventually it'll flood over the boundary of this potential well, which are given by the dashed lines. And you will have you will enter a new world. So that's actually the regime which we call global chaos. This is a very interesting regime. So let me just say some of our results. So if F naught, the macro potential is strongly convex, C2 and L smooth, then under some assumptions, the limiting distribution of the iterations of phi will actually converge. Well, the iterations of phi will converge to some statistical distribution, and we can actually characterize this distribution. It's nearly Gibbs distribution with a density given by the one in blue. I mean, I will not talk about the justification, but rather the implications. So what does this mean? So, okay, so the actual loss function may be something like this. Okay, so macro potential polluted by a lot of micro local potential wells. But the actual limiting distribution only depends on F0, not F1. So, therefore, if you sample from the corresponding Gibbs distribution, you will basically get something like red. Okay, so your initial distribution may, so suppose you start with an ensemble of initial conditions that are distributed according to this blue distribution. After sufficiently many iterations, the distribution will become like the red one. If you change the initial distribution, you will still converge to the red one. But the point is the red one doesn't see all those local minima. It doesn't see any of them. So therefore, when the learning rate is large, you can actually escape from the local minimum. This is like, so if you are on this landscape, you are driving a car and you are driving very fast, you don't feel those small pebbles. You don't feel those small bumps anymore. You just feel the large scale potential. So in machine learning, people really care about escape from local minimum. They traditionally think that this is due to, you can have escape because you have stochasticity in the gradient. That certainly works. But in this case, we showed that a large learning rate can do the job as well. So it's a completely alternative mechanism. You don't need any noise. Okay, non-convex, I've not, let me skip that. So instead, there is a practical problem. So you may say, okay, the theory is nice, but do we have multi-scale potential? Do we have multi-scale loss functions in reality? In reality, The answer is yes. So here is some empirical result. For example, so here, if you do very long time iterations, so you do many iterations, and then here is a parameter of your state, or if you prefer, a parameter of your neural network, you actually not converge to a point. You converge to this blob. What is this blob? It's actually corresponding to a statistical distribution. So let me skip some details, but just to say that, okay, so we have empirical evidence and we also have partial theory. So the intuition is very very natural. So in neural networks or supervised machine learning in general, you have training data, and you want to basically minimize the loss function that are based on this training data. If your training data has some multi-scale behavior, which is usually the case because the data usually corresponds to fluctuations around some mean, and fluctuations may be much smaller, so you can have some multi-scale structure in the data. Maybe the loss function can actually inherit this multi-scale property. And if you think about this, this is not trivial because the loss function is a function of the parameters. It's not a function of the data. The data is already given to you. But we can do some actually derivations to show that if you just have two layers and you use a periodic activation function, then you can really inherit the multi-scale structure. So yeah, sorry. So that's why we also have some theoretical evidence that if you use a large learning rate in neural network, you can really get convergence to a statistical distribution rather than just a point. So to summarize, chaotic dynamics can actually happen in gradient descent if your learning rate is large enough. And when that happens, you can actually escape small-scale local minima. And the reason is because in this case, the dynamics is no longer optimizing the loss. It doesn't converge to the minimizer. Instead, it actually converges to a statistical distribution, and the iterations are effectively sampling from this statistical distribution. So you can have a quantitative way of escaping from local minima. Why this matters? Again, this way you have higher probability of going to deeper minimum, which means better training accuracy. And oftentimes, better training accuracy corresponds to better test accuracies. So this matters a lot. Okay, finally, I'll talk about another perspective. So the previous discussion was mainly on training accuracy, and now I want to talk about generalization. So the gap, so the difference between training and test accuracy. And in fact, in machine learning, a folks' wisdom is that if you converge to a minimizer that has flatter local geometry nearby, then it gives you better generalization. So I will not prove this or say anything about it, but assume because of that you like flatter minimizing. And in this work, again with student Yuqing Wang, former student Ming Shuo, and faculty collaborator Tuo Zhao, published at another top machine learning conference. We wanted to actually rigorously show that if you have a large learning rate, then you basically will pick flatter minimizers. So that's what the long title means. So let me first talk about a little bit about the setup, and I will try to finish in time. So what is a neural network? So suppose you have a two-layer neural network. Basically, it has a loss function given by this. W1 and W2 are weight matrices. Sigma is something called an activation function. So, the traditional activation function sigma, so something people use very often is called a ReLU function, which is basically this function, max of 0 and x. So it's a piecewise linear function, and it has a special property called homogeneity. So what that means is that, okay, so if you multiply the input by a constant scalar, the output is going to be scaled by the same scalar. So even if this is a highly nonlinear function, you have homogeneity, which can be inherited by the loss function. And in fact, W1 and W2 are matrices, but you can easily convince yourself that if you multiply W1 by a scalar and divide W2 by the same scalar, then you will get the same value of the loss function. That's because of the homogeneity of this sigma function. So you have this nice symmetry, which gives you a lot of amazing structures. For example, you have a continuous set of minimizers of F. Okay, so you give me a minimizer. I can find in an arbitrarily small neighborhood another minimizer. So you really have a continuous set of minimizers. But the funny thing is, some actually generalizes better than the others. So maybe the flatter ones will generalize better than the others. So here I'm not doing any statistical machine learning theory. So I'll just see whether I can get flatter minimizers. So do we get those? Do we get flatter minimizers after training? So it depends on what kind of optimization algorithms you use to optimize F, and it depends on what is your learning rate. So also one thing that a disclaimer is that you may say, okay, so this is a two-layer neural network. Why do you call it deep learning? So unfortunately, that's the status of the field. So the theory is lagging behind the applications. So people typically just analyze 2 layers, even though of course that's not enough, but it's already non-trivial enough. And in fact, people sometimes even analyze something called a 2-layer linear neural network, in which you actually drop this activation, and of course you still have homogeneity. To see that even 2-layer linear neural network is non-trivial. Another popular problem in data science is called matrix low-rank factorization. So you are given an n by n matrix, n may be very big. You want to approximate this matrix by a low-rank matrix, and what you can do is you can formulate an optimization problem where x and y are unknowns. They are n by d, and d is much smaller. And then you try to find x times y as your approximation, and you look for the best approximation that approximates a, so that minimizes the distance. And these two are almost the same problem. So 2-layer neural network, linear neural network, and low-rank factorization. So I will be, for the sake of clarity, just focusing on the matrix low-rank factorization. This problem has a lot of interesting features. So for example, every local minimum is a global minimum. But they, as I said, there are infinitely many of them, and they don't generalize equally. In fact, some of them will have, almost the same. Some of them corresponds to almost the same norms of x and y. In this case, we will call such a point to have a balanced norm. Some of them actually has very different norms of x and y. And you can easily prove by just computing the Jacobian and then evaluating its eigenvalues that if you have a minimizer that has balanced norm, then the local geometry is flat. So now the question is, if we use gradient descent to minimize this function corresponding to nonlinear iterations given by this, will I converge to a flat local minimum, or in this case, flat global minimum, or a sharp global minimum? So there are technicalities that, literature that are very important, but I'll skip. Basically, the literature only focused on the h going to 0 limit, because then you can use gradient flow as a tool. We want to study large h. And our observation, and in fact, proved result, is that if h is very big, you can have eventual balancing, meaning that, okay, you can start with initial conditions that correspond to very different norms, but eventually you will converge to a point where the norms balance. to show you a picture, okay, so this is a toy example. So this is actually a one-dimensional matrix factorization. It's just a toy example, but it can be visualized. Okay, so A in this case is just a scalar 1. Matrix X is a scalar X. Matrix Y is a scalar Y. So this is just a two-dimensional optimization problem. I can visualize the dynamics in 2D. And what is this curve? So this is actually the set of minimizers. So I mean, if X times Y is equal to 1, then of course you have a minimizer. So you can easily see, you have a continuum of minimizers. If you look at this minimizer, the one that intersects with the diagonal, of course, this corresponds to X equals to Y equals to 1. And this is where you have balance. If you are, say, right here, you have bad balance. So Y is very small, X is very big. Now, if I start at the cross, that's my initial condition, and I do gradient descent with a small learning rate, then you can barely see it, but basically you will follow this red trajectory. You will converge to a nearby local minimizer. If your gradient descent uses a large learning rate, very interestingly, you will not converge to this local minimizer. You will follow this very perplexing trajectory and eventually converge to a flat minimizer that is almost like X equals to 1, Y equals to 1. Okay, so this is something we can prove. Yeah, other technicalities. So this is basically saying that you cannot use any traditional optimization theory. You lack regularity. I mean, you don't have global licentiousness, and your learning rate is too large, etc. So let me skip all the details. But also also there's another experiment where I'm trying to show that what I just showed was not specific to 2D. Here, you can do large matrix factorization. I mean, in this case, you can have hundreds of dimensions, in fact, thousands of dimensions. You get the same phenomenon. So if H is very small, the balance in between the two variables, X and Y, in terms of their norms is terrible. So their norms barely change. But as H becomes larger and larger, as you move to the left, you get better and better balancing until, at some point you get instability, and then the gradient descent iteration actually goes up. So I don't think I can talk about the proof, but basically, you have to scrutinize the discrete dynamics, and that's why, we like dynamics. So let me summarize. Okay, so if you use a large learning rate in gradient descent to work on homogeneous problems, then you actually have this implicit bias. It's actually created by your algorithm. Well, so the choice of a large learning rate is part of your algorithm. So you have this implicit bias which favors more balanced solutions, and more balanced solutions is equivalent to flatter minimizers in our case. So you have actually a provable preference over flatter minimizers. Okay, so I realized that I was pretty fast. We actually wrote a blog. So it's this GitHub blog. It's dynamic. If you scan this QR code, you can go there. So it's hopefully a nice introduction of some of the things that I talked about. And because we just started doing this very recently, we were told that if you do machine learning, you have to be social. So you cannot just stay in your office. So we even created a Twitter account. So if you like what we do, please follow us. We will be providing more and more cool things about dynamics and machine learning over there in plain language. Okay, so that's it. Thank you very much. And I cannot do these works without my amazing students. So let me acknowledge them. And of course, thank you for your attention and feedback.
Thank you very much, Tao. Let's thank our speaker. And we're out of time, but maybe if let me stop the recording.